In some cases, a circuit that's designed to operate at low frequency can emit high-frequency RF signals. Frequently, this can happen because of poor printed circuit board design techniques. For example, driving a 50 MHz digital communication signal across a gap in the ground plane can cause RF emissions. If these emissions leave the printed circuit board and travel through the air, they are considered to be radiated emissions. On the other hand, if the emissions travel through a cable, they would be considered to be conducted emissions. RF emissions can be picked up by other circuits and impact the circuit's performance. A circuit subjected to the RF emissions may be sensitive or insensitive to this issue. For example, a long PC board trace or cable can act as a good antenna and be especially susceptible to RF pickup. The degree to which a circuit is sensitive to RF pickup is called RF susceptibility or immunity of the circuit. Finally, it should be noted that some circuits will intentionally radiate, whereas some radiation is unintended. For example, a cell phone is designed to transmit RF signals, so it is an intentional radiator. On the other hand, the digital communications we mentioned previously was not intended to radiate RF noise. One of the main goals of this content is to provide methods to minimize the unintended emissions and improve the immunity of circuits to RF noise. This slide shows how a 10 MHz digital square wave can have frequency content to GHz. Technically, the waveform we are considering here is a trapezoid wave, as the waveform has finite rise and fall times. The Fourier theorem states that any repetitive signal can be represented as an infinite series of sinusoidal waves called a Fourier series. The Fourier series for the trapezoidal waveform is shown at the right. The frequency of the square wave is 10 MHz. This means that the Fourier series will have a fundamental component at 10 MHz, then will have frequency content theoretically to infinite frequency. Fortunately, the harmonic content decreases rapidly so that, from a practical perspective, the harmonics are very small at high frequencies. Analyzing the Fourier series will show that the roll-off of the harmonics is 20 dB per decade for frequencies just above the fundamental, then increases to 40 dB per decade at higher frequencies. The point at which the attenuation changes from 20 to 40 dB per decade is considered to be the RF emissions bandwidth. After the bandwidth limit, the harmonics are considered to be insignificant from an emissions perspective. The bandwidth is calculated by taking 1/pi times the rise time. Thus, the rise time of the square wave is a key factor that determines how far in frequency the harmonic content extends. Both square waves shown here have the same fundamental frequency, but have different rise times. The first example has a fast rise time of 1 nanosecond, and the bandwidth limit is 318 MHz. The second has a slower rise time of 5 nanoseconds, and its bandwidth limit is 64 MHz. Later, we will see measured results that show RF emissions for different rise times. Here we present equations for velocity and wavelength for electromagnetic waves for printed circuit boards. The velocity is determined by dividing the speed of light by the square root of the relative permittivity of the PC board dielectric. FR4 is the most common dielectric, and it has a permittivity of 4.5. This number is not well controlled, and it can vary significantly. Higher frequency boards often use better controlled dielectrics such as Johnson. In any case, applying the equation for FR4 dielectric, the velocity is 1.414 times 10 to the 8th meters per second. The wavelength of an electromagnetic signal is determined by dividing the velocity by the applied frequency. So for a 10 GHz signal, the wavelength is 14 millimeters. The wavelength is important in PC board design as it's an indication of how good a trace or cable acts as an antenna. Traces that are multiples of a quarter wavelength make good antennas. Traces that are shorter than 1/10 of a wavelength are considered to be short from an RF perspective. We will refer back to these equations throughout this presentation. One of the key concerns is that we do not want to create unintended emissions for our PC board designs. Unintended emissions can happen when long PCB traces act as antennas. Also, it's important to have a continuous ground plane beneath your PC board trace. If there's a slot in the ground plane, as shown on the right, this can cause emissions. We will discuss this in detail later, but for now, I want you to know that any structure that works well as an antenna for emissions will also work well as a receiver. The principle that an antenna will work equally well as a transmitter or receiver is called reciprocity. Keep in mind that when we cover PCB design problems that cause emissions, the same design may also create noise immunity issues. In the example above, driving a digital signal across a split in the ground plane will cause emissions. Placing a low-level analog signal above a split isn't likely to cause emissions, but through reciprocity it will act as a good receiver and pick up RF noise. Finally, if you wanted to create an intentional transmitter, such as a Bluetooth device, one way to create an antenna is to drive a signal across a split in the ground plane. The picture on the left is a Vivaldi PCB antenna where a signal is driven on the top layer across a split in the ground plane. Note how similar this structure is to the unintended antenna. We will return to the example of driving signals across gaps in the ground return path, as it is one of the most common EMC design errors. Here are some basic printed circuit board layout definitions. The figure on the left is a 4-layer PCB with a top and bottom layer as well as 2 internal layers. Generally, the internal layers are reserved for ground and power planes, and the outer layers are used for signal traces. The functional order and number of layers on a PCB is called the stack-up. So, for example, a 4-layer board may have a stack-up of top equals signal, inner 1 equals ground, inner 2 equals power, and bottom equals signal. The layers in a PCB are separated by a fiberglass insulative material called dielectric. The most common dielectric material used is FR4. Higher frequency designs may require more expensive dielectrics, such as Johnson, but we will only cover FR4. A PCB core is a rigid dielectric material with 2 copper layers on top and bottom. A 4-layer board is built by adding thin sheets of dielectric material called prepreg on the top and bottom, followed by a top and bottom layer of copper. An important point here is that the core thickness is generally large compared to the prepreg thickness. Thus, the top and bottom layer are very close to the inner layers. This is important from an EMC perspective. Beyond understanding the basic PCB construction, it's important to understand a few common PCB geometries. The microstrip is a single PCB trace above a copper plane, and the strip line is a PCB trace placed between 2 return planes. The length and width of the trace, as well as the dielectric thickness, will impact various PCB characteristics such as impedance. We will refer back to the microstrip and strip line configuration throughout this material. This slide shows a typical mixed signal system. A low-level analog signal from a bridge sensor is applied to an instrumentation amplifier, which is followed by a high-speed op-amp. The op-amp drives an analog-to-digital converter, which is connected to a precision voltage reference and microcontroller. In this system, look for rapid transients as the most likely noise sources for RF emissions. The digital I/O signals, the reference input, and the analog-to-digital converter inputs all have switching transients associated with them. There are many techniques that can be used to minimize noise. For example, taking care to make sure that the ground return path is continuous is very important. Proper layout and selection of decoupling capacitors is also useful for minimizing noise. From a digital perspective, minimizing overshoot and reflections reduces noise and crosstalk. The sensitive low-level analog may not be a source of noise, but it can be easily corrupted by noise, causing large measurement errors. Minimizing trace length for low-level signals and keeping them away from transients can help prevent noise coupling. Using differential lines and proper filtering can also reduce the impact of noise on analog devices. Throughout today's presentation, all of these concepts will be discussed in detail with emphasis on proper PC board layout. I built and measured some PCB experiments to support the theory in today's presentation. The experimental results will be discussed in detail throughout the presentation. Here I do a brief introduction to show the hardware and discuss the measurement methods. Two different categories of experiments were developed for this content. One type of experiment uses a full analog signal chain similar to what was previously introduced. This circuit is duplicated multiple times with the same schematic but different layouts. The idea here is to compare good versus bad layout methods to show how the analog performance, RF emissions, and RF susceptibility are impacted. The second category of experiments are looking at digital communications. Typically, a long trace is driven by a digital signal, and the performance impact of trace spacing, grounding, and via placement on crosstalk and emissions is considered. This slide shows the real-world test equipment used for the experimental results in this presentation. To provide a good high-frequency oscilloscope connection, a probe socket is used to connect to an SMA connector. To measure RF emissions, EMI sniffer probes are connected to an RF amplifier and a wide bandwidth spectrum analyzer. The sniffer probes measure the near-field RF emissions on the PCB. Sniffer probes are good for locating a source of RF emissions on a PCB. For product EMI compliance testing, far-field RF emissions will be measured using an antenna in an anechoic chamber. We will not cover this today, but the reference section provides a link to an excellent application note covering many of the different compliance tests. That concludes this video. Thanks for watching. Please try the quiz to check your understanding of this video's content. Question 1. Which would have higher frequency emissions? A 10 MHz square wave with a 1 nanosecond rise time, or a 50 MHz square wave with a 5 nanosecond rise time? The correct answer is A, a 10 MHz square wave with a 1 nanosecond rise time. Remember that the square wave will have frequency content out to high frequency. The rise time of the square wave will determine how wide in frequency this content will spread out. The equation 1 over pi times the rise time can be used to estimate the upper frequency limit of the square wave. Question 2. What kind of EMC problem would you expect with the low-level DC analog signal? The correct answer is B. It may act as an unintended receiver. Question 3. True or false? Reciprocity states that a structure that works well as an antenna for transmitting will work equally well as a receiving antenna. The correct answer is A, true. For this reason, low-level signals are susceptible to RF pickup, and higher-level AC signals may act as unintended transmitters on PCB structures that act as unintended antennas. Question 4. What is the wavelength for a 100 MHz frequency on an FR4 PCB? The correct answer is C, 1,414 millimeters. To make this calculation, first calculate the velocity by dividing 300 million meters per second by the square root of the dielectric coefficient of the PCB. In this case, the PCB is FR4 and it has a dielectric coefficient of 4.5. The velocity in this case is 1.414 times 10 to the 8th meters per second. The velocity is then divided by the frequency of the waveform to find the wavelength, which is 1,414 millimeters in this case. Question 5. What is the minimum PCB trace length that would make a good antenna for a 100 MHz frequency on FR4 PCB? The correct answer is B, 354 millimeters. This question is related to the previous question. In the previous question, we determined that the wavelength for a 100 MHz signal is 1,414 millimeters. A good antenna is a multiple of a quarter wavelength. Dividing 1,414 millimeters by 4 gives 350